Hello, everyone. So, today in the GOCC, we have Andrew Reimer-Berg from Colorado State University, and he'll be talking about slide trees, caterpillars, and permutation pattern avoidance. Before that, we should remember our GOCC guidelines. We're all learning, everyone has something to contribute, and no one has all the answers. And with that in mind, take it away, Andrew.
Thanks, Aditya. I'd like to thank all the GOCC organizers for inviting me. And so, so I'll be talking about some research I've been doing the last year or two involving various types of trees that are motivated by combinatorics of some geometry. And so specifically about slide trees, caterpillar trees, and how permutation pattern avoidance fits into all of this. Okay, and so I'll start with just a little bit of geometry background. The geometry is not really not that important for this talk. And so it is interesting, but it's not important for the talk. So if you don't know what any of these things are, don't worry about it. But if you are familiar, this will give some additional context. So one geometric space that people have been studying a lot lately is the moduli space of stable curves. So I use that, denote that by M0 n plus 3 bar. And so one thing geometers really like to do is, given some space, it usually has some cohomology ring, and then people multiply, compute products of various classes that live in the cohomology ring. And so in this case, M0 n bar has these classes called omega classes. And so Leslie Griffin Levinson in 2002 showed that if you take some particular product here, let's see, can I do a laser pointer? Can you see my cursor?
Yes, we can.
Great. Yeah, so if you take this product here in the cohomology of M0 n plus 3 bar, that gives you a number that is the same as the cardinality of this slide omega of k, or the cardinality of this set tournament of k. And so that reduces a complicated geometric problem into the combinatorial problem of counting how many objects are in a set. Okay, so the first important thing here to say is, what is this k here? So it is a composition of n, by which I mean it is a tuple with n parts, where the sum of all the parts add up to n. And they're allowed to be 0, but they have to be non-negative integers. And then this composition must satisfy what we call the reverse Catalan condition, which means the first j entries, the first I entries must add up to at most I for all I. So for example, if n equals 3, our allowed compositions are 1, 1, 1, 1, 0, 2, 0, 1, 2, 0, 2, 1, or 0, 3, 0, 0, 3. So they have to add up to n. We can't have a 0 in the last component, or else we'd have too much in the first two. The first entry has to be a 0, 1. So these are the only possibilities we have. So anything like 0, 3, 0 is not allowed. 2, 0, 1 is not allowed, and any other ones that aren't up there aren't allowed. Okay, I see a question in the... Yes, it's a weak composition. I guess I should say, if you have any questions, feel free to ask them at any time. I'm happy to clarify things as we go. Okay. And so if K is not a reverse Catalan composition, both of these slide sets are the empty set, and so the product back in the geometry land is 0. I should stop here and say, as a combinatorialist, one particular thing on this slide really stands out, and that's this equality here. We have two different sets that for any parameter k are always the same size. And so my instinct is to say, okay, can we show that combinatorially? That is, can we find a bijection between these two sets? And so that's the problem that I've been working on. Okay, so big picture, we have this set tournament of k, we have the set slide k. We want to find a bijection between them. And so the intermediary object we'll be using to build this bijection is going to be some set of words. And I have that in quotation marks because I haven't really said which set of words it is there. There's a lot of different sets of words, but that's going to end up depending on what our composition K is. So it's going to be potentially be complicated. So like if K is all ones, so 1, 1, 1, 1, 1, 1, which is a case I'll talk more about later, then words really means permutations on N. Other times it might be set of all words with content K. Other times it's going to be some restriction of that set. And so there is actually a known bijection between tournament of K and words using column restricted parking functions, if you've ever heard of those. If not, don't worry about it. So that means our focus is really, went too far, to find a bijection that turns these slide trees into words, classify which sets of words those are, and piece everything together. Okay, yeah, so that's the overarching picture. So now let's talk about what these slide trees actually are. So slide omega of K is a set of trees that are trivalent, meaning every vertex is either a leaf or has degree 3. And then we label the leaves by A, B, C, 1, 2, 3, ... N. And we also require that A and B are adjacent to the same interior vertex. So as an example of that, here we have A and B are adjacent, and then we have C, 1, 2, 3, 4, 5, 6, labeling the other edges. And then I'm claiming that this is in slide of 0, 0, 2, 1, 1, 2. And so this isn't actually a definition. It's not every tree of this form. There's going to be a condition there's going to be a process to check whether a particular tree is in a particular slide set. And so technically they're defined a different way, but this is the way I work with them because it's more intuitive and it's easier to check, okay, is this thing actually in the correct slide set? I guess the other thing I should mention going back here that makes this problem particularly interesting is, so tournament of K is also a set of trees that have that satisfy the same characterization. But the difference is if you create a tree that satisfies these properties, it's going to lie in exactly one tournament set. So the tournament sets partition the set of all such trivalent trees, whereas the slide sets instead are sort of maximally overlapping. Given some tree, it could live in more than one slide set. It might lie in none of them. Yeah. Right, yeah. So you could think of it as not requiring, or yeah, I'm not saying this right. Same as non-planar binary trees. Yeah, another way you could also think about it is like just treat A and B as itself a root, but then we relabel that as splitting it off as A and B. That would, I think, be a third way to say the same thing. Yeah, so for example, this tree here where we have A, B, C, 1, 2, ... N minus 1 and N on the other end, that's in every slide set for all K where that makes sense. So for every reverse Catalan composition K, that is a composition of N. So that makes finding these bijections complicated because some things are in multiple slide sets, some aren't in any. So here's how we actually check. And so I'll do that in this example, check that this slide tree is in this slide set. Okay, so start with L is equal to N. So in this case, L is 6. And so we're going to start by sliding 6. So the first step of each round is to contract labeled edges. I haven't labeled any edges yet, so we don't do anything. Next, we want to choose the next edge to label. And so we let E be the first unlabeled internal edge on the path from L to A. So starting at 6, we go along the tree towards A. This is a leaf edge, so we don't count that one. The first internal edge is this one that I have highlighted here in red. So I'm going to see if I'm allowed to label that edge 6. And so to check that we're allowed to do that, we have to compare the smallest label on each side. So on the side with 6, I just look at the smallest leaf label on that side. So that's 1. On the other side, I look at the smallest leaf label that is not on the branch coming off of here as A. So I should also say with this alphabet, I think of A is less than B is less than C is less than 1. And so we don't count this whole branch here because that's the branch with A. And so instead I look at the smallest thing here, which is C. And then I check, is L greater than I is greater than J? So in this case, 6 is greater than 1 is greater than 6, C. And so the slide's valid. I go ahead and label that edge 6. And then I will need to iterate. So if L is labeled K sub L edges, we decrement L, otherwise we keep going at the same L. So in this case, K of 6 is 2. That means that 6 is going to need to label 2 separate edges, and we've only done 1 so far, so we're going to have to do 2. And so now I do that again, where now I treat the edge that we labeled 6 as being contracted. And so now this is contracted, so the 6 is really here, and so the smallest thing on this side is now C. The smallest thing on the other side that isn't A is B. B is less than C is less than 6. So again, we're valid. We can label that one 6. Now 6 has labeled 2 edges, and so 6 is done. We go down to 5. And so the edge that 5 is going to label is the first one from 5 towards A. That's this one highlighted here in red. And so now when we think about what we're comparing for the labeling on the side of this edge, that's on the same side of this edge as 5, C is the smallest thing. But on the other side, we're excluding the branch containing A. But again, these 2 edges here are contracted. And so really, we can think of this whole thing as one blob of a vertex that has 4 leaves jutting out from it, A, B, 6, and 1. And so when we exclude the branch containing A, we're just excluding A itself. And so B is then the smallest thing on that side. And so B is less than C is less than 5. We do that label. 5's done 1. That's all we need to do. And then it goes similarly. So 4 compares 2 to C. That's good. C 3 goes from 2 to C, and then from C to B. And so the process terminates and labels all the edges. And so that verifies that, yes, this tree is in the given slide set. Any questions about that process? How we do that? I had to look at it several times before I really understood what was going on. Okay, I guess I should also say that here I'm slightly abusing notation by talking about this tree as being in the slide set with the edge labels there. Like the edge labels aren't actually part of the definition of the tree, but I have them there just because it's going to be really useful going forward. Okay, and so now before I get to more results about classifying these trees, I need to take a diversion and talk about permutation pattern avoidance. Okay, so we say that a permutation sigma contains another permutation pi if sigma contains a subword that has the same relative order as pi. Conversely, a permutation sigma avoids a pattern pi if it doesn't contain it. So if it contains no subword with the same relative order as pi, then sigma would avoid pi. So as an example, 14352 contains the pattern 123, because if we look at the subword 135, that 135 has the same relative order as 123. Conversely, 35214 avoids 123 because no matter which subword of 123 you choose, it's not going to have that relative order. And so we can extend this idea to words as well as just permutations, both on the sigma side and on the pi side. So here we can also say that 24665346 contains 1221, because if we look at the subword that I have underlined here, 4664, that's the same relative order as 1221. Some other variants that we're going to need is barred permutations. So now we allow our pattern pi to have some of its entries barred. And so now for our sigma to contain a barred permutation pi, it must have a subword that has the relative order of the non-barred portion of pi that is not a subword of the entirety of pi. So the way I think about that is the bar is indicating for this pattern, to have this pattern, there must not be a thing in the position with a bar. So for example, 1, 2, 3, 4, 5, 6 contains the pattern 2, 3, bar 1, because it has, like, choose any two of those that has the same relative order as 2, 3, and there's no subword of 1, 2, 3, 4, 5, 6 containing those two that is also a 2, 3, 1. Right? There's nothing down here, so there's no way to form a 2, 3, 1. So every 2, 3 is a 2, 3, bar 1. Conversely, 2, 3, 4, 5, 6, 1 avoids 2, 3 dash 2, 3 bar 1, because every instance of a 2, 3, I choose any 2, 3 I want up here, that is also part of a 2, 3, 1. And so it does not have that pattern. I'll leave that up for a minute for you to stare at that, since I think these are pretty confusing.
Oh, yeah. So the okay, I don't know. I haven't thought of this enough, but how does the bar exactly act? So if I have two, one bar, or just one, two bar, three bar, then I'm saying there should be no 1, 2, 3, or there should be no 1, 2, or and not a 1, 3. Like, how does the like two bars? How do they like, is there like an and condition on the two bars? How
Like
how would
if
it?
the like 1, 2, 3, where 2 and 3 are both barred.
Yes. How would that work? Am I not even allowed a 1, 2, or is that allowed?
I'm not into. I've only seen this used. I've only actually needed this where there's only one bar in your pattern.
Okay.
If you had
Okay.
more,
Okay,
yeah, I
that's
don't
fine.
know if it's an. I don't actually know if it's an and or condition.
Hmm.
I don't
Okay.
know if the definition at the top of the slide is paraphrased, but from the definition at the top, it would indicate that it needs to, like, you just forget all the bars and you check it is 1, 2, 3. Like the definition is just the subword of all of pi.
Hmm.
And so that would indicate 1, 2 isn't a problem. It's only 1, 2, 3 that is what you ignore when you're checking for subwords of 1.
I see. I was thinking of it as 1, 2 bar, 3 bar, but it's actually 1, 2, 3 bar then. Okay.
Maybe.
Okay. If it's only
I
one
mean,
bar, then it's fine. Then it's okay. It's fine. I know. We can
I'm
talk
sort
about
of
that later.
cheating here a little bit, where I found this behavior and then was like, is there a name for this? And found someone else in another talk elsewhere that used barred permutations.
Hmm.
And so I was sort of borrowing their notation. So I don't recall them using multiple bars either, but I could go back and double check. So I would have to double check the exact definition for how these work. But for my purposes, there's only ever going to be one bar in a pattern. And so it's
Okay.
containing a barred pattern is containing a subword that is the non-barred portion. So in this example, the 2, 3, that does not have an entry where the bar is. Right, yes. Okay, and then the other variant of pattern avoidance we have is more straightforward, I think. We're also going to impose some adjacency conditions. So for now on, we'll use a dash within our pattern to indicate entries that do not have to be adjacent, and any entries that don't have a dash between them must be adjacent. So for example, if our pattern is 2, 3 dash 1, that means it's a 2, 3, 1, where the 2 and the 3 are adjacent. So 3, 2, 5, 4, 1 contains 2, 3 dash 1 because the subword 2, 5, 1 is a 2, 3, 1, and the 2 and the 5 are adjacent. On the other hand, 4, 3, 1, 5, 2 avoids 2, 3 dash 1, because even though, like, if I look at the subword 4, 5, 2, that is a 2, 3, 1, but the 4 and the 5 aren't adjacent, and so it doesn't satisfy the requirements. And then for some notation here, if we have a set of permutations or set of patterns P, we write av sub k of P to denote the set of words with content K that avoid every pattern pi in P. And more commonly, you'll see this where you're just working with permutations, so where your content is all ones, and that's usually av n of P. I see another question in the chat. Yes, I'm not barred from redefining it, but I thought I might as well use notation that exists instead of creating two notations for the same thing. But yes, I appreciate the joke. Okay. Any questions there before I move on? Great. Okay, now caterpillar trees, the third thing in my talk. And so a tree with the shape, we call a caterpillar tree, right? Because it's like a line with a bunch of legs. And so we define the subset of slide that is the caterpillar trees as cat omega of k. And so this is very useful because it turns out that in a lot of different things we've been working with these slide trees, proving things first about the caterpillar trees and then building up inductively has been very fruitful. And so in the first case, I promised earlier we'd talk in detail about the case where k is all ones. And so in that same paper I mentioned earlier, Gillespie, Griffin, Levinson showed that the caterpillar trees where k is all ones composition are in bijection with the permutations that avoid 2, 3-1. Right, so for example, and so the way this bijection works is if you perform the slide algorithm on your tree, well, if it's a caterpillar, your internal edges are a path. And so you just read off the labels for the edges from the root to the other side. So here, if we have this tree down here, we perform this. We slide every label once. We end up with edge labels as is above. And then we just read off 5, 2, 1, 4, 3, 6. And sure enough, that is a permutation that avoids 2, 3-1. And so that's going to turn out to be our base case for building the full all ones case. Yeah, so our goal is to define a map phi that goes from the set of permutations Fn to the set of all slide trees 1, 1, 1, 1, 1, 1. And so I won't give the full proof because it's several pages long and it's messy, but I'll give at least the idea for how we define this map. And so given some permutation sigma, if it avoids 2, 3-1, well, then it's just the corresponding caterpillar tree, since they also prove that there's exactly one caterpillar with each such permutation as its edges. But otherwise, if it contains a 2, 3, 1, we denote the earliest instance of a 2, 3, 1 by XYZ. So when I say earliest, I mean greedily choose of all the 2, 3-1s, the one with the earliest 2, 3, and then of those with that 2, 3, choose the earliest possible one. And then we can write sigma as T, X, Y, U, Z, V for some words, T, U, and V. And so from how we chose this, well, because we chose it to be the earliest one, TX avoids 2, 3-1. And then this is sort of the diagram of how we would build that. So TX avoids 2, 3, 1. So we can think of that as a caterpillar. So it's kind of like we have a caterpillar where instead of just having two leaves at the end, we have two more trees that are inductively the same map on shorter permutations. And so that's sort of where the induction comes in. We're inducting off of, I guess you'd say, the number of 2, 3-1s in our word, or if you were going the other direction in the bijection, this would be inducting on the number of interior vertices of your graph. So like number of vertices that are not adjacent to any leaf. Like this one right here would be one such. And then, yeah, we just do that recursively. So if within here, if YU has a 2, 3-1, you'd take the earliest one. The first part would be a caterpillar here, and then it's branch off again, so on. And so if we want to reverse this map, well, we just start by labeling all the edges of their tree, and then start at the root, start reading off. When we get to somewhere where it branches, this branching would necessarily correspond to a 2, 3-1 somewhere in the permutation we're building. And so we're going to read off, or so one of the two edges going off of the branch will be larger than the other one. And so we'll read off the entire branch with the larger one first, potentially having multiple steps in there. Then we jump back and do the entire one with a smaller one. And so let's look at this in an example. So suppose we have the pattern 8, 5, 3, 7, 6, 9. Oh, I'm sorry, there's a 9. 4, 2, 1. Then phi of sigma would be this tree down here. And so, well, first of all, reading it off, how that would go, yeah, we start the root, we go 8, 5, 3, and then we have either the 7 or the 2, the 7's larger, so we do this entire branch. 7, 6, oh no, we have another branch. And so we do the larger one, the 9 first, we do 9, we finish that branch, we jump back to the previous vertex, we do 4. Now we jump back again, we go back to here, 2, 1. Okay, so that's the inverse map. That one, given a tree, it's not too hard to read off labels. Going the other way would be a little more complicated. So we start, the earliest 2, 3-1 is the 3, 7, 2, right? 8, 5 decreases, so that can't be a 2, 3-1. 5, 3 also is, and so the earliest increase is the 3, 7, and then the earliest thing smaller than 3 is the 2, so that's the earliest one. And so yeah, we just build these 3 edges here, and then down below that, the ZV part is the 2, 1, so that's again just another caterpillar going off down below. And then to the right, this whole thing here is phi of 7, 6, 9, 4. And so we do, again, that one has a 2, 3-1 in the 6, 9, 4. And so we do 7, 6, and then recursively we have a 9 and the 4. And so that builds the whole tree. And so again, I'm sort of cheating here where I'm building the tree by the edges and not the leaf labels. And so the tricky part of the proof is that in this case, building the edges this way will have a unique way of recreating leaf labels so that doing the slide algorithm gives us the corresponding tree. And so, yeah, so I was able to prove this map I've described here does give us a bijection between Sn and slide omega 1, 1, 1, 1, 1, 1. Any questions here about this? Yeah.
Could you go through the direct example again once more?
This one? No, which example was that?
So you did the reverse bijection, right? Can you do like the direct bijection once more? The one where you start with a composition and then read it off the tree, that one. So the reverse bijection is where you find the 2, 3, 1 and read it, right? Then you create the tree. The other one, I kind of just missed that.
Yeah, so going the other way, you basically start with the tree, you create its edge labels, and then start at the root, which is, I think of the root as being where A and B are, and just read off the edge labels going down the tree. When you get to a branch, the edge at the start of each branch has a label. One of them is larger than the one you just read, one smaller. So it's like the 3 versus the 1 in a 2, 3, 1. And so you do the 3 branch first, followed by the 1 branch.
Okay, cool.
Yeah, so going the other way, you do 5 or 8, 3, 5, and then all of this branch here, and then all of this branch here. And actually, the most tricky part of all of this was just showing that the map I've written here is well defined. So if it's not clear why that actually gives us a slide tree, that's a good question. It is quite complicated. Okay, and so this case where k is all ones, that's one case down. There's one other case that isn't interesting. If our composition is 0, 0, 0, 0, 0, 0, 0, n, well, then then all of the sets in question are size 1. Bijections between singleton sets is really easy. Okay, that's another case. But all the other cases in between, they can get a lot more complicated. And so the next case that we sort of bit off was for when k is right justified. And what I mean by that is the composition k consists of a bunch of 0 entries followed by a bunch of non-zero entries. So let's see, if I go all the way back to when I first gave a bunch of compositions, the right justified ones be 1, 1, 1, 0, 1, 2, 0, 2, 1, and 0, 0, 3. This 1, 0, 2 would not be right justified because it has a 0 after a non-zero. Okay, let's go back. Okay. And so what I was able to show was to give a pattern avoidance condition that characterizes the caterpillar trees whenever k is right justified. So in general, if k is right justified, then the caterpillar trees are in bijection with the set of words with content k that avoid 2-1-2 and 2-3-barred2-1. Okay, I'll pause there for a second to piece together what that means. So avoiding 2-1-2 just means that in our word, any time a letter repeats, everything in between has to be larger, weakly larger. Like you can't have a 6 here and a 6 here and then something smaller in between. And then 2-3-barred2-1 means we have a 2-3-1 where between the 3 and the 1, we don't have a 2. Or conversely, here we're avoiding said pattern. And so to avoid that pattern, that means if we have a 2-3-1, then there must be a 2 between the 3 and the 1. Let's see, I'll say that again. So to avoid 2-3-barred2-1, that means every 2-3-1 must have a 2 between the 3 and 1. Yes, question? Sorry.
No, I was trying to figure it out
Okay,
in the
yeah.
air. Yeah.
Yeah, so for example, the word 3-6-7-6-3-5-4, first of all, avoids 2-1-2 because the 2 6s only have a 7 between them. The 2 3s only have things larger than 3 between them, so it avoids that one. And then it also avoids 2-3-barred2-1 because even though 6-7-3 or 6-7-5 or 6-7-4, those are all 2-3-1s, they are not 2-3-barred2-1s because of the second 6 right here. It's like the presence of this second 6 prevents us from having a problematic pattern. And so, yeah, so this word avoids these 2 patterns. And then the tree, there's this tree here where we give those edge labels and build the leaf labels necessary. It is in cat omega of 0, 0, 2, 1, 1, 2, 1. Okay. And so if you stare at this hard enough, you'll see that this criterion here is a generalization of the earlier one in the all ones case, because, well, if k is all ones, well, then you can't have a 2-1-2. And so since you don't have repeats, not having this 2 here, specifying that doesn't matter because that can't happen. So you then just have to avoid 2,3-1 entirely. And so we recover the earlier case. Questions there about that?
Can any avoidance of a bar permutation be stated as having a given permutation?
As in, can we restate this as, instead of it doesn't have this, it does have
Yeah.
something else? Not really, at least not in any of the ways I've looked at it, because like
Oh, I
you can,
see.
like you could always have 1, 2, 3, 4, 5,
Okay.
like you could always arrange them in
Mhm.
increasing order, and then there's
Okay.
there couldn't be a
Cool.
2, 3-1 at all, so it doesn't matter if you have a 2, 3 dash bar 2-1 or not. Or
Okay.
if you have all decreasing, like arrange them in weakly decreasing order,
Mhm.
it's going to be the same thing. So like avoiding this thing would
Right.
never guarantee that you have any other particular pattern.
Awesome. Yeah,
And
that makes sense.
I think that would hold in general, but it definitely holds in the patterns I'm
Yeah.
looking at.
Okay, cool. Yeah, this makes sense.
Okay. Yeah, so that's at least the caterpillars of a much larger case. Can we go any further? And so that I'll talk about a little bit about where we've tried to go since then and some of the complications that come up. So for all ones composition, we started with the caterpillars and then built a bijection for all of the trees in that case. So can we do the same thing for the right justified case? We have a characterization of the caterpillars. Can we build a bijection between all the slide trees where K is right justified and the set of all words with content K? And so one of the difficulties there is in that earlier case, we took a tree, we found its edge labels, and then we built a map just based off of the edge labels. But here, so this is on the left, we have the tree we had earlier. On the right, I have the same tree where I swapped the labels 2 and 1. And so if you spend a little time with that, you'll see it still satisfies the slide labeling algorithm. And moreover, you get the exact same edge labels that we had with the other tree. And so here we have 2 different trees with the exact same edge labels, and they're in the same slide set. And so that means that in general, the trees are not purely determined by their edge labels. And so that means the tools we've used so far alone are not going to work. And so there's some other ideas that show a lot of promise, but we don't have complete results there yet. So I'm not going to say a lot more about that. The other direction one could go is to characterize all the caterpillars when K isn't necessarily right justified. There, again, it gets more complicated because it's no longer becomes just pattern avoidance, right? So like, if I had had time, I would have drawn up an example here where you have 2 different trees where like the edge labels have the same relative orders, so it has all the same patterns, but one is a valid slide tree and the other isn't. So that's another further complication. We do also have, like I just found some stuff like last week that shows a lot of promise here, but again, we don't have any full results there. Okay, and I guess I talked a little bit fast since that's all I had prepared. So I'll thank you all for listening to me talk, and I'll be happy to answer any questions.
Let's thank the speaker. Hey, that was a great talk. Do people have any questions? Yeah. So also one thing I don't know if I completely missed that. So what exactly is the omega part? Is it from geometry?
Why are there omegas everywhere just hanging around that I never talk about?
Yeah.
So I guess I could have omitted them for the sake of
Oh,
this talk, but technically they are important there. It's because this
yeah.
omega right here.
And is that something you can tell? Yeah, like, is that
Yeah,
like
so
something
there's
that?
actually two different cases in the geometry land. There's taking products of omega classes, and there's
Hmm.
also taking products of psi classes. So psi is a different class
Okay.
in the homology of our moduli space. And so that one, if you put a psi here, well, there's not a corresponding thing for determinant trees, which I haven't talked about. So
Hmm.
get rid of the third thing in this equality. But if you make this a psi here, there's also slide psi trees. And so you just put a psi here.
Hmm.
And
Okay.
so actually that distinction isn't that important in the right justified case, because it turns out that the slide, if k is right justified, slide omega of k and slide psi of k are exactly the same. Combinatorially, what happens when you have a psi there is that in this step here, you just get rid of the L is greater than or equal to condition. So you no longer care that the thing you're sliding is larger than the two things you're comparing. You just care about the comparison. So in the right
Interesting.
justified case, that doesn't actually change anything. In other cases, it allows you to have a larger slide set.
Hmm.
Yeah, so notationally, it's important because there are actually different types of slide sets. But for this talk, I only talked about one of them, so I never really talked much about omega.
I see. Also, have you looked at the? So, what other special case have you looked at? So, like right justified and the 1-1-1-1 case.
Right.
Are there anything like you have examples for that might be, easier to do?
Yeah, so I thought some about how to break
Like
things
just two
down
numbers or
more.
something?
Like, I mean, I have lots of like small cases of
Yeah,
things. Uh, like I have a whole notebook full of just doodles of trees and trees and trees and trees.
yeah.
Because like the thing is they grow large quickly, but they grow large faster than problems show up. Like I've countless times had a conjecture for something that doesn't work. And then like the
Mm,
first counterexample I find is like n is one too big for me to have exhaustively already looked at that case.
yeah.
It's like n
Yeah.
equals 6, maybe there's 30 trees or 45 trees maybe. But then if I go up to n equals 7 for whatever case I'm looking at, suddenly there's like 210 trees. And I don't have the time to write out 210 trees by hand.
Yeah, that's fair.
But yeah, I've spent time looking at small cases and have some ideas. Um, the thing is like the thing that makes non-right, like for generalizing right justifiedness, the thing that makes non-right justified things complicated seems to be the same issue no matter which non-right justified thing you look at. And so I'm not really sure if there's a good way of breaking that down further other than having to go
Mm.
to all the caterpillars just because it seems like it's the same issue that shows up in any case.
So it's the zeros in the middle that are the issue.
Yeah, it's having a zero that's larger than a non-zero means that you're trying to slide a label when there's larger leaves hanging around that don't, because like in the slide algorithm, you start with n and work your way downwards. Like you slide larger labels before smaller ones. And so when you don't have any zeros in the larger end of things, that means every larger, like by the time I is sliding, every larger label's already slid. And so in some way that sort of gets them out of the way. And so that doesn't become an issue when you're making your comparisons. But if you have a
Mm.
zero, right, like, so let's say n is 6 and we have a composition that ends in 0, 2. So 6 slides twice and 5 doesn't slide at all. Well, that means, say when I get around to 4 sliding, since 5 never slid, there's still a 5 leaf label hanging around.
Mhm.
And depending on where that leaf label is, it might throw a wrench into trying to have 4 slide, for example. That might make more sense if I could draw, but I don't know if there's
Yeah.
an easy way of drawing right here.
Yeah.
I
But
guess I have a
roughly
white
it makes
maybe.
sense. Yeah. Are there any other questions?
I have a question.
Yeah.
I like the theorem on the slide. It's facing us right now. This bijection. I want to know, can this slide algorithm answer questions about traditional pattern avoidance and those famously tough four pattern things like 1, 3, 2, 4, things like that. I guess that's one part of the question. The second part is like, where have we seen the slide algorithm in general? Is there a larger context within which this has been studied? Does it come up in, I don't know, combinatorial representation theory or something like that? Does it, where would we have seen it? Because it feels familiar. It sounds familiar. I can't remember where I've seen it. Is it RSK, something like that? I don't know. I guess my
Right, yeah.
question is, can
Okay,
you say a little
so
more about the slide algorithm in its larger context?
yeah, so for the first question, I'm not sure how this, like maybe there's a way to answer pattern avoidance questions here. I'm not aware of them because like we kind of start, like the way this project goes, maybe this will go some way towards answering your other questions. Like if I go back to this original paper here, so this paper from 2002 is, from my knowledge, is where
2022.
they defined these slide trees.
Okay.
And like the way the slide out, I said that this slide algorithm here isn't actually the definition for these. It's sort of just like an easier way of checking that a particular tree is in a particular slide set. The actual definition can also be phrased combinatorially, but really originates from the geometry of doing this product formula in cohomology ring of this geometric space. And so it's like doing a bunch of this geometry gives us these combinatorial objects. It's somewhat analogous to RSK. Like RSK allows us to count tableau, and sometimes tableau arises from looking at products in the cohomology of the Grassmannian. It's sort of analogous here, where instead here we're looking at cohomology of moduli space, and the objects that arise that we need to count are how many trees satisfy these properties. And then if we're looking further at these trees, well, they found this, I won't go back to it right now, but they, in the other theorem from that paper I put up, where the caterpillars in all one's case avoid 2, 3-1. I don't think anyone was going into this expecting to see pattern avoidance. Is this, it kind of showed up organically, which I think is
Understood.
really cool.
Yeah,
and so
I
it's
guess
like
that's what
there's
I wanted to
certain,
know. Yeah, thanks.
yeah.
No, by all means, finish your answer. But yeah, I understood what you meant. Yeah.
Yeah.
Okay. So let's thank the speaker again. Okay. I will stop the recording now.